Hey guys, hi, welcome back to another video. Today we are going to see how we can implement UNet architecture with the help of PyTorch in Python. So today I'm not going to cover everything in detail, but I'll try to teach you all of the things in a theoretical way verbally as we go. Okay, so without any delay, let's get into the architecture and the ever famous diagram of UNet architecture. So here you can see from the shape of the architecture, it has received its name called UNet because it looks in the shape of a U. Okay, so it's a very simple architecture, but it can be very complicated for somebody who's looking at it for the first time. So let's go ahead and try to understand what is happening inside of this architecture. There are two main operations going on here. Well, fundamentally there are 5 different main operations that are going on, but if you try to summarize everything, then there are 2 main operations going on. One is downsampling and the other is upsampling. Okay, so if you look at the arrow marks here, the red arrow mark, well, not just the red, but the combination of 2 blues and 1 red can be considered as a downsample. So from this one block, I'm downsampling it into this smaller block. From this, I'm downsampling it into an even more smaller one, much more smaller one from that, and then I'm doing a simple operation here. This line, this one particular line, can be called as a bottleneck operation. Okay, so this doesn't fall completely under downsampling and doesn't fall completely under upsampling, so we call this as bottleneck. And after that, we've got an upsampling, another upsampling, another one, and another one. Okay, so what exactly is happening inside of each of these operations is what we are going to discuss today. Now if you look at the arrow marks here, this legend, whatever we have here, is pretty much what we need to understand the whole architecture. Okay, now forget about the last operation here. Con 1 into 1 is not something that we are going to focus on. This is only for the final output layer, but put that aside for now, and put both of these up and down arrows aside for now. But first, let's just take a look at the blue arrows. Okay, so here you can see there are 2 blue arrows. Each of these blue arrow is indicating a convolution layer. Okay, which means here I've got 2 different convolution layers. Here I've got 2 different convolution layers. The same thing here, 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 and here, 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 here. Okay, so whenever we are doing any kind of a downsampling, we will apply 2 convolution layers. The same goes with upsampling as well. Whenever we are doing an upsampling, we need 2 convolution layers. Okay, so this pair of 2 convolution layers is what we call as double convolution. Okay, so this double convolution plays a very important role in every single layer here. You can see that here we have a double convolution, double convolution, double, 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 double. Okay, so every time we use a convolution, we don't use one of it, we always use double convolution layers. Okay, so keep these terms in mind: double convolution layer, downsampling, upsampling, bottleneck. Okay, so far these are the terms that I've used, so try to remember these terms, because in the coming few slides we are going to use the exact same words to create our classes and functions. Okay, now when it comes to downsampling, there are 2 different aspects to this. One is the convolution, the double convolution part. The moment you do the double convolution, you'll have to follow that by 2 different aspects. One is going to be your pooling. Okay, so you will do some kind of pooling, maybe average pooling, maybe max pooling, it's up to you, but according to the original paper they are using max pooling, so I am going to use max pooling for this implementation. But basically the idea is, after doing a convolution, after doing a double convolution, you will apply max pooling and you will bring the size down. Okay, and after the every double convolution, you will follow it by a max pooling. This is only for the downsampling part. Okay, when you're coming down, 2 convolution layers is always followed by a single max pooling. Not only that, but you will also use the output of the double convolution in the future when you're upsampling it. Okay, now, so I hope this downsampling part is clear. It's very simple, guys. Okay, one double convolution followed by max pooling, one double convolution followed by max pooling, one double convolution followed by max pooling. Okay, it's very simple like that. Now when it comes to upsampling, we will take the previous output of the convolution layer, output of the double convolution. We will upsample the output of the present layer's double convolution, and we will concatenate them. Okay, if you see this one here, it's much more clear, right? Okay, so let's assume that I am currently at this level. Okay, now I'll take the output of the double convolution, which is this block, okay, this rectangle here, and then I'll concatenate it with my previous level's double convolution output. Okay, I'll be following the exact same pattern for all these layers. So if I'm doing it for this layer, I'll take the double convolution output, I'll take the double convolution output for previous layer. Okay, so this block and this block will be concatenated together. The same thing here, output of double convolution of this layer concatenated with output of double convolution of the previous layer. Again, after doing the concation, I'll simply pass it through one more double convolution, and then I'll do the opposite of max pooling. So what is opposite of max pooling? Max pooling is where you will reduce the size of the image, but in up convolution, there are two different ways of handling this actually. So when I say max pooling, there is one more pooling called average pooling. So both of these things do the exact same thing. They will try to reduce the size of the image. Similarly, in up convolution, this green arrow, there are two different ways of doing it. One is upsampling, the other one is convolution transpose 2D. Okay, so convolution transpose, there are two different ways of doing it. They have implemented convolution transpose, and that's why you see the up conv here. If they used upsampling, then there would be upsamp or something like that here, but basically the original paper is using convolution transpose. So to reduce the size of the image, they are using max pooling. To increase the size of the image, they are using convolution transpose. Okay, now I hope this architecture has been clearly explained to you, and if I have to recap it, double convolution followed by max pooling, 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 and then we have reached the end of downsampling. Now double convolution followed by upsampling, and then concat the previous layer's output. Double convolution followed by upsampling, concat with the previous layer's output. Double convolution followed by upsampling, concat it with the previous layer's output. The same thing again. Okay, so to do this, again, if you observe the pattern here, it's very much simple. There is so much of repetitiveness going on here, so we are going to try to use functions for this. Now I am going to create three different classes. First class is called double conv, second class is called downsample, so third one is upsample. These are three different classes that I will need. Let's take a look at double conv. Okay, so here we got double convolution layer, here. Okay, so every time I need to perform double convolution, I'll make use of this class. Again, whenever I want to do a downsample, which is this part, okay, only this part, then I'll go ahead and use the downsample function, and whenever I want to do an upsampling, I'll go ahead and use the upsample function. Okay, now one thing that you have to keep in mind is, when I say downsample, I don't mean only this arrow mark, but these three arrow marks combined. So which means my downsample will contain the double convolution and the max pooling. My upsampling will contain double convolution and upsampling. Sorry, the double convolution and convolution transpose. Three operations. So when I combine three of these operations, or three of these operations, or three of these operations, they fall under downsampling. When I combine these three operations, they are upsampling. These three fall under upsampling. Okay. Now, if you look at the forward functions here, double convolution will always take only one layer, one input. Downsampling will also take only one input. But when it comes to upsampling, I need two different inputs, x1 and x2. That is because whenever I'm doing an upsampling, this will be my x1, and I'm going to concatenate the previous layer's output, which is going to be my x2. Okay, so whenever I do an upsampling, I am combining both of them. So I'll need x1 and x2. Okay. So these are the three most important different functions that we are going to use for the architecture. Now let's take a look at double conv. Okay, this plays a very important role in terms of the whole architecture designing, because it's been repeated at almost every single layer. Now let's see what is happening inside of it. First thing is I'm importing the nn.module module here, so all of the torch properties will be imported. Now I'm creating a sequence, and within that sequence I've got two convolution layers, just like how the architecture talks about it. Okay, this is relu, which is just an activation function, so obviously we don't have to mention about the activation function here, and instead of relu you can go ahead and use some other activation function as per your requirement. But according to the original paper they have used relu, so I went ahead and used relu here. But the main concept here is we are using two convolution layers, and whenever I pass any input, okay, during the forward pass, whenever I pass any input to this convolution operation, it is going to pass through both of these convolution 2D layers. Okay, now let's take a look at what exactly are the channels and what is the shape, how am I handling all these shapes. If you see here, every time I do a double convolution operation, my number of output channels remain exactly the same. 64 twice, 128 twice, 256 twice, 512 twice. The same thing here, 1024 twice. I don't know why I didn't draw a box here, but 512 twice, 256 twice, 128 twice. Okay, so every time I do a double convolution, I have to maintain the exact same output number of channels in both of my layers. Okay, so that is the reason why my output channels remains the same in both of these layers. Okay, so that is about convolution block, double convolution block. Now let's go ahead and understand the second most important one, which is the downsampling. When I go into downsample, okay, so this is my class called downsample, and over here I am creating two different variables. One is the conv variable and the second one is pool. Whenever I have to do convolution operation, as I said, downsample is not just this downsampling part, but a combination of one double sample followed by a max pooling. Okay, the combination of one double convolution followed by a max pooling. So two blue arrows, one red arrow, two blue arrows, one red arrow. Only when you combine two blues and one red, that's when we call a downsample, which is exactly what I'm doing here. So I have two different variables. One has an object called conv, which takes directly the double convolution that we have explored just now in the previous slide, and one more which is called max pooling, where I'm using max pool 2D function from PyTorch. Okay, now in the forward pass, I'll take my input, I'll pass it through double convolution, Then I'll pass it through the max pooling operation. After passing it through the max pooling, I've got P. After passing it through double convolution, I got down. So I'm returning down and P, both of them. Again, remember, every time I do a downsampling, I need two outputs. One is this gray arrow, which I'm going to use later on, and one is this red arrow, which I'm going to use in the next layer. Okay, so that's the reason why I'm returning two of these things. Now let's go ahead and understand what is happening instead of upsample. Again, in an upsampling, first thing that you have to do is convolution transpose, which is what we have here, convolution transpose, and then you will follow that by a double convolution, right? But before doing that, you will simply concatenate the previous layer. So what counts as an upsampling is one green arrow followed by one gray arrow followed by two blue arrows. Okay, so one upsampling, one concation followed by double convolution, which is exactly what I'm doing here. I'm defining two different objects. One is called up, one is called conv. Again, I'm using the exact same double conv class that I've created, that I've shown you just now. This one. Okay, so this double conv will be used for both down and upsampling, and also for the bottleneck, by the way. Yeah, we'll cover that when we reach there. But when it comes to the upsampling part, here you can see upsampling starts here. So one green arrow, which is the up part. So I'm taking x1 and x2. I'll take x1, I'll pass it through the upsampling. Whatever result I get is going to be this variable, which is a tensor. I'm going to concatenate it with x2. Okay, so this is just an axis. So after doing the concation, then I'll pass it through my convolution layer. Okay, I hope this is very simple and easy to understand right now. Okay, now that we have created downsampling and upsampling, let's go ahead and create the whole architecture together. Now here I've created 4 different layers, 1, 2, 3 and 4, 1 bottleneck and 4 upsampling layers, 1, 2, 3 and 4. Okay, now let's see how we can use it in the forward pass. Here I've got down convolution 1, down convolution 2, 3, 4. For every one of them I've got down 1, down 2, down 3, down 4, which is these gray arrows, P1, P2, P3, P4, which are these red arrows. Okay, now bottleneck. What exactly is this bottleneck? Bottleneck is just a simple double conv again. Okay, now I'll take an input, I'll pass it through the first double convolution. Whatever I get after the pooling, I'll take that pooling, I'll pass it to the second double conv. P2 will go into third layer, P3 will go into fourth layer, P4 will go through the bottleneck, which is just a double conv, and after that I'll take the output as B. I'll take B here, and whatever I had in my previous layers convolution output, I'll pass it as x2. So if you remember, what is x2's purpose? X2 will be concatenated. Okay, after doing the upsampling, I'll concatenate it with the x2 and then I'll pass it through double conv. So I'll take B, which is the bottleneck output, I'll upsample it, then I'll concatenate it with down 4 and then I'll pass it through a double conv. Whatever output I get there will be up1, up 1, and I'll repeat the exact same process for the whole up convolution. Okay, once I do all of that, I am simply creating one output layer, which is a convolution 2D, and input channels is 64, output channels is the n number of classes, whatever number of classes that you are currently dealing with, and you can customize this final layer as per your requirement. So that's why I've put it at the very bottom separately. but the general idea and the general implementation of this architecture can be found in these layers. Okay, I hope this code is easy for you guys to understand right now. Now, this is a simple data set that I've created. So if you guys want, link will be in the description. You can go ahead and explore the GitHub page and understand how exactly am I trying to implement this model. But basically I've created a dataset, a class called caravan dataset, which is importing all of the uh, dataset module from PyTorch. And in the initialization function, I've got my root path where I have the current file, current .py file, current this code sitting in, and then I've got one boolean called test or train, test, which is going to indicate if it is a testing class or a training class. Okay, now I'll be using this dataset twice. That's the reason why I've given this as a boolean function. So as long as the test is equal to false, it will go into this into the else part, and if it is true, then it will go into the if part, and the only difference is just the path. Okay, so instead of each of these variables, instead of each of these if and else blocks, I'm simply writing the code as per the training and testing path. And my transformations are basically just resizing. Okay, since my very first layer of the architecture takes where is this? Okay, so for the dataset, I'm taking transforms.resize and I'm resizing the image into 512 by 512, and then I'll convert that into a tensor. Okay, pretty simple. So that is about the init function. And next I've got get item. So whenever I pass an index for this object from the images, if it is training, it is training path, if it is testing, it is testing path. So from the images, I'll take an image, and I'm using pillow library here to do image.open. Okay, I'll take that image, I'll convert that into the respective RGB channels, then I'll pass it through the transform function. I'll do the exact same thing for the mask as well, and I'll return both of them. Okay, I don't have to explain the length function, it's pretty self-explanatory. But yeah, basically in the get item, I'm taking one image and its appropriate mask, I'm passing it through the same transformation function, which is simply resizing it and converting that into a tensor, and then I'll return both of them separately. Okay, so this is about my data set. Now let's go ahead and see how we can do model training. Okay, here we are in the model training. So I've given my hyperparameters here, not this. So these three would be my hyperparameters, and the rest of the things are just some hard coding and of course my device. Okay, here you can see I've created a class for my training data set. I didn't pass anything for the test boolean. Where is this? Yeah, here you can see I didn't pass anything, which means by default it's going to take false. So obviously this is going to be the training data set. I'll take my training data set and I'll split it into an 80-20 rule, 80-20 portion using the random split function. It's directly available in torch.utils. And once I split it, I'll create a data loader for that. I'm simply passing the splitted data set along with the batch size shuffle equal to true. The same thing for validation data loader as well. Okay, so here I'm creating a data loader for training and validation. Next is model. Of course, the same model that we have explored until now. This part. So if you see the init function, the only thing that I really need here is input channels, output number of channels, number of classes. Okay, that's what I'm going to pass here. Input channels are going to be 3 because this is going to be an RGB image. Number of classes is going to be 1 because I'm going to use this model for image segmentation. Again, device agnostic code, just a simple thing. I'm using Adam optimizer here, BC with logic loss, basic stuff. For epoch, in range of epochs, I'll set the model to training mode, and I've created a variable called train running loss equal to 0, and throughout the training I'll calculate the appropriate loss, and then I'll keep adding it into this variable, so that once I finish going through one batch, I can calculate the training loss of that batch. Sorry, once it goes through all the batches in an epoch, I can calculate the training loss of all those batches. Okay, and then until now my model is in train mode. Now I will put it into testing mode, evaluation mode. With torch.noGrad, I'll take my validation and I'll do the exact same thing. I'm retrieving my image and its mask, and I'll predict, I'll calculate the loss, I'll accumulate the loss, and I'll calculate what exactly is the current loss for this epoch. Now I'll print training loss for epoch number and what is the training loss, epoch number and what is the validation loss. Once I do this for the epoch count, here I've given just 2 epochs. So once I do the whole training for both of those epochs, I'll save my model. Okay, this is a very basic implementation of a UNet training, but I really hope you guys were able to understand how we can construct the UNet architecture from the paper directly and how simple it can be. I hope you guys have enjoyed this video. I tried to wrap this up real quick without wasting any time, and I think I was able to finish it within just 28 minutes. So yeah, thank you for watching. Have a nice day.